I also in a research. If you come across a research profile, she had a very long profile in research, nearly 100 papers published in uh, reputed national, international journals, and also she's a reviewer uh, for a journal called Enrich, and she had participated in many webinars, seminars, workshops, and have attended um, more programs, which means she had a thirst of uh, learning. Even at, after completing 32 years of experience in teaching, 11 to 12 years of experience in research, she's still having the thirst. That's remarkable, ma'am. And it's the main thing we, the budding researchers, have to get it and follow your pathways. So, on behalf of our research department, I thank for accepting our invitation to be a resource person for this faculty development program. With this note, I hand over the session to today's resource person. Please, ma'am.
Thank you, Ms. Jackson, for giving me the introduction. Shall I share my screen?
Yes, ma'am, please. Yes, ma'am.
Yeah,
Your
it's
screen
black.
is visible now. Uh,
Um,
could you please make it a slideshow? Then it will show in the full screen. That's why. Or in reading view. Anything is yes, ma'am. Yes,
okay.
that's super, ma'am. Thank you. Please, ma'am.
Okay, okay. Thank you very much. First of all, I wish to thank the management and the principal and all the head of the Department of Mathematics of V.O.Chidambaram College, Dr. Nagarajan, my supervisor, and I wish to thank all the members of the Department of Mathematics of VVCC for giving me this opportunity. My topic, actually, the topic for today's program is especially matrix theory. So if we take, we have, though we have many branches for mathematics, all those branches are interrelated. We all know that one. And this speech, I thought of connecting algebra and graph theory. So in graph theory, we are having many of us know what is a graph and what is matrix. So from matrix, we are having the characteristic polynomial, characteristic equation, and solving the characteristic equations, we have eigenvalues. So those eigenvalue concepts are converted to or taken to the graph theory. So for graphs, we are introducing energy of graphs in terms of the eigenvalues. Actually, the introduction, that is the graph theory energy concept, was introduced by Ivan Goodman in the year 1978, but he himself is motivated from a paper he published in 1930 related to chemical graph theory. That is, that the person is theory, that is, which is named Huckel molecular orbiter theory, is very famous in chemistry. Even they are having a syllabus in chemistry. syllabus as a important factor. That is actually this Huckel's method allows chemists to calculate actually 5 electron orbits if they are studying with, then going through that theory introduced his he introduced this one in the paper, energy of gravity in 1978. So energy of a gravity means, as mentioned here, this is related to and also to this with the map one. So first of all, let us collect some algebraic concepts. A is a square matrix, then the equation determinant of A minus xi is equal to 0 is called the characteristic equation of the matrix A. This we all know. And solving this characteristic, some of the eigenvectors, the trace of A and is along main diagonal. So now connecting this to graph theory. We all know is A and B are adjacent. So from the adjacent, we name we give the entry as one matrix. So the number of vertices, if you mention as P, then it is a and along the columns, the vertices. So V1 to V1, if you take V1 is not adjacent to V1, that is, there are no loops. We are considering only simple graphs, there are no loops. So V1 to V1, there is no adjacency. So we take the entry as 0. Again, if you take V1 to V2, in a path, the second vertex is adjacent to first vertex and third vertex. So the second entry is 1. Third entry, it is not adjacent to 0. So V1, first row corresponding to V1. So V1 adjacent to V2 only. So V1 in the first row corresponding to V2, we are getting 1. And if you check the second row, it is corresponding to V2. V2 is adjacent to V1 and V3 alone. So corresponding to V1 and V3, we are having 1. All other entries are 0. So similarly, we are proceeding. So the adjacency matrix of the path P5 looks like this. So now we are having a matrix. So corresponding to the matrix, we can think of the characteristic polynomial. So the characteristic polynomial is the characteristic polynomial of the graph. We are defining as the characteristic polynomial of its adjacency matrix determinant of characteristic polynomial of the graph is f of gx, which is denoted as f of gx is, if we are saying polynomial, there will be no equal to 0. That is type of gx is equal to determinant as an equation, then we put it is equal to 0 equation, and we can find the roots of the characteristic equation, and those roots values. So solving this determinant of A minus xi is equal to 0. If A is the adjacency matrix, as I said already, by P. So solving a polynomial of order P. So we are using for eigenvalue. Lambda 1, lambda 2, etc. Lambda p the lambda. So if you take the spectrum of the graph, we can represent in this form. That is, the spectrum of the graph is spectrum of theta. So here M1, 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 M2, etc. MP. MIs are the algebraic multiplicity of the eigenvalue lambda I. For example, if you are having just a 5 by 5 matrix and we are having two eigenvalues, 5 by 5 matrix we are solving and we are getting three eigenvalues, first and second repeated twice and the third one only once, then we will get only, though it is a 5 by 5 matrix, we get only lambda 1, lambda 2, lambda 3. Lambda 1 occurs 2 times, so M1 is 2. Lambda 2 occurs 2 times, M2 is 2. Lambda 3 occurs once, so M3 is 1. So this is the representation for spectrum. Now, using spectrum, we are going to define the energy of graphs. So the energy of a graph is defined as the sum of absolute values of lambda I. So sum of absolute values of lambda i's. That is, in mathematical representation symbols, we can write E of G. The notation we use for energy is E of G. E of G is equal to sigma I is equal to 1 to P modulus of lambda I. That is very, very important. Absolute value of lambda I. Now, when we are finding the trace, just we are adding. Okay. But here we are finding the modulus, sum of the modulus. Next, a lemma, that is to find the characteristic equation. This lemma may be used. Suppose B is a matrix which could be represented in the form B0, B1, B1, B0. That is blocks of matrices. We are having two blocks of matrices of same order. That is also very, very important. Two square matrices which are block matrices and they must be of same order, and the overall matrix can be represented in the form B0. Hello.
Ma'am?
Hello. Am I audible now?
Yes, ma'am. Yes, ma'am. You are audible.
கேக்குதா?
கேக்குது மேம். இடையில அந்த
இவ்வளவு நேரம் கேட்கவே
நெட்வொர்க் இல்ல, இல்ல.
இல்லை.
நீங்க சொன்னது எல்லாமே கேட்டுச்சு மேம். இடையில உங்க நெட்வொர்க் ப்ராப்ளத்தினால
ஆ,
ஒரு சிஸ்லிங் மட்டும் இருந்துச்சு. நீங்க வீடியோ ஆஃப் பண்ணிட்டு பேசுனீங்கன்னா, ஆடியோ வில் பி
ஓகே.
வெரி கிளியர். டெக்னிக்கலுக்காக.
ஆ, ஓகே, ஓகே.
ஓகே மேம். மத்தபடி உங்க ஸ்க்ரீன் எல்லாமே
பட்
ப்ராப்பரா
ரெண்டுமே
இருக்கு
வேற
மேம்.
வேற. ஆ, ஆ, ஓகே.
நல்லா இருக்கு மேம். தேங்க் யூ
Now it
மேம்.
is
தேங்க் யூ.
okay.
எஸ் மேம். எஸ் மேம்.
ஆ,
கிளியர்லி ஆடிபிள். தேங்க் யூ மேம். தேங்க் யூ
ஆ,
மேம்.
okay. So we to find the matrices characteristic polynomial, we can use this form. If we are having B as a matrix, which is having 2 by 2 block matrices, that is B0, B1, B1, B0. If you are able to write the original matrix in this form, where B0, B1 are square matrices of equal order, then the spectrum of matrix B is the union of spectrum of B0 plus B1 and B0 minus B1. So here the union means just we are writing the spectrum of B0 plus B1. That means eigenvalues of B0 plus B1 first, followed by the eigenvalues of B0 minus B1. So now the energy of a graph is calculated for some graphs, that is for a complete graph Kp. E of Kp is equal to 2 into P minus 1. Now to calculate this one, we are writing what is the adjacency matrix of Kp. The adjacency matrix of Kp, if you take in Kp, every vertex degree is P minus 1. So except along the diagonal, all the entries are equal to 1. Along the diagonal, we have 0. All other entries are equal to 1. So the matrix can be represented in this form also. That is Jp minus Ip. And Jp is the matrix with entries 1. All entries 1. And Ip is the matrix with 1 along the diagonal alone. So along the diagonal, 1 minus 1. So along the diagonal, 0 by 2. The remaining entries are the ones. So along the diagonal 0, all other entries are 1. So the matrix can be written in this form. Its polynomial, if you are finding f of kp comma lambda is of this form. Determinant of a minus lambda I. Actually, this is calculated and written. It is equal to lambda plus 1 power p minus 1 into lambda minus p minus 1. Now, to find this value, we can use MATLAB. So, in MATLAB, we can write a program. We will see that one later. So, using MATLAB, we can find the polynomial. Just if we are writing the matrix, entries of the matrix, giving the order, then we can find the corresponding, we can directly get the characteristic polynomial. So, once we get the characteristic polynomial, we can solve the equation, characteristic equation. So from this one, we are able to find lambda plus 1 is a repeated root, which is repeated, lambda plus 1 is equal to 0, p minus 1 times, so which gives minus 1 as a repeated root, p minus 1 times. And lambda minus p minus 1 is equal to 0, gives the root lambda is equal to p minus 1 once. So we are writing the spectrum of Kp as minus 1, p minus 1 times, and p minus 1 only 1 time. So now the energy is the sum of modulus of or absolute values of the eigenvalues. So minus 1 absolute value is added p minus 1 times. Absolute value of minus 1 is added p minus 1 times. That means 1 is added p minus 1 times. So p minus 1 plus p minus 1 is added 1 time. So 2 times p minus 1. So the energy of Kp is actually equal to 2 times p minus 1. Similarly, for a complete bipartite graph, the energy is found. Again, here the form is written, the adjacency matrices. Here, if you take the complete bipartite graph, we partition the sets into vertex set into 2, V1, V2. Then the elements of V1 are all adjacent to complete bipartite. So the elements of V1 are all adjacent to the elements of V2, and the elements of V1 are all adjacent to the elements of V1. So we are getting, and there are no edges in between the elements of V1 and the elements of V2. So vertices of V1, if you are corresponding to just V1, V1, here also V1, V2, etc. Vm and U1, U2, etc. Un. Suppose V1 is having m elements and V2 is having n elements, then row wise m plus n elements and column wise also m plus 1 elements. So if you are taking the m plus 1 elements, first m elements corresponding to, we get 1 0 matrix, and for the remaining we'll get a matrix with all entries 1. Similarly, here also all entries 1, which can be represented also as J transport. And here again there are no entries within the elements of the matrix, so we'll get zeros. So now this is the matrix. Again, if you substitute, actually in MATLAB we can write a program PQ, we could give values. So corresponding to the values, we'll get the corresponding polynomials. So we can generalize those polynomials. So generalizing the polynomial, we are getting lambda power p p plus q minus 2 into lambda square minus pq. So this polynomial when solved, we are getting lambda power this one. So this is equal to 0 gives 0 is the root p plus q minus 2 times. And so taking this is equal to 0, lambda square minus pq is equal to 0, we get lambda square is equal to pq. So lambda is equal to plus or minus pq. So plus or minus root pq. So plus root pq one times and minus root pq one time. So this is the spectrum. So energy that is left out, I think. So the energy is the sum of these things. So 0 added this much number of times gives 0, and modulus of this one gives pq root pq and again plus root pq. So 2 times root pq, which is the answer. And this is for star graph. Similarly, for star graph, if you take the root vertex is adjacent to every other vertex, but all other vertices are non-adjacent within them. They are adjacent only to the root vertex. So the matrix looks like this. That is 0, and here a matrix in which whose order is 1 cross p minus 1, 1 by p minus 1, and here all entries are 1, here all entries are 1, and here all entries are 0. So this matrix, when again we are using MATLAB, we are getting lambda power p minus 2 into this one. Solving this, 0 is a repeated root p minus 2 times, and lambda square is equal to p minus 1 gives lambda square minus p minus 1 is equal to 0 gives lambda square is equal to p minus 1, and lambda is equal to plus or minus root of p minus 1. So 0 is a repeated root p minus 2 times, and root p minus 1 1 times, and minus root p minus 1 1 times. So on addition we are getting 2 into root p minus 1. Similarly, we could find for path and cycle. These are the results. Now some results are connected to the eigenvalues. Let G is any undirected simple graph with p vertices. Then sigma I is equal to 1 to p, lambda I is equal to 0, and sigma I is equal to 1 to p, lambda I square is equal to 2q. The first one is simply actually sigma is equal to 1 to p, lambda I. The sum of eigenvalues, we have seen in the beginning itself, the sum of eigenvalues is equal to the trace, which is actually the sum of diagonal entries. So here the sum of diagonal entries, if you take sigma is equal to 1 to p, aii, here each aii is equal to 0, since no vertex is adjacent to itself. So a11 is 0, a22 is 0, etc. So each entry is 0 along the diagonal. So if you are finding the sum is also equal to 0. Therefore, the sigma I is equal to 1 to p, lambda I is equal to 0. And the second factor is sigma is equal to 1 to p, lambda I square is equal to 2q. Here we take the sum of squares of the eigenvalues of A is the trace of A of G square, that is squares of the eigenvalues. So we take A square matrix, that is A into A. So A square matrix, there you find the eigenvalues, that gives the sum of squares of the eigenvalues. So here we are taking sigma is equal to 1 to p, lambda I square this. Here we have to consider the product matrix. So the product matrix, this is the form of the product, as we all know. So matrix product, A, B, if you are having two matrices, then sigma is equal to 1 to k, the corresponding rows and column elements we write, and Aij into Bik, like that we used to write as well, Bjk, Aij into Bjk, if the order differs, if the order is the same, then here both are A matrices, so we are taking sigma is equal to 1 to p, sigma is equal to 1 to p, Aij into Aji. So here I is equal to 1 to p. So equal values of I and j are also appears. We separate them. So separating the equal values, we get I is equal to j. So Aia square plus the remaining is I not equal to j, Aij into Aji. And sigma is equal to 1 to p, Ai square. This is the trace. So we are getting this is 0 plus the second one, if you take I is not equal to j, Aij, Aji. If we expand this one, actually A11 into A21, A12 into A22. So like that, actually A11, sorry, not A11, A12 into A21, A13 into A31. So like that we have all the entries. So if we take that one, Aij is same as Aji, since the matrix is a symmetric matrix. So here the transposes itself. So Aij is same as Aji. So you can write this as I less than j, Aij square, and here we can combine Aij, A12, A21. Okay, A12, A21. We can combine both the we are getting two terms. Twice appear ago. And J repeat agumbodhu, we get the same value. So 2 into, we are putting Aij the whole square. So it is equal to 0 plus 2 into the modulus of, sorry, 2 into E of G value. This we already proved, isn't it? Aia square. So we are having 2 into, sorry, this is not the energy, this is the number of edges. Aia square. Why we are writing this as the number of edges? Actually, here we are taking Aij into Aji. How many times we will get 1? That is, if I is adjacent to J, if the vertex Vi is adjacent to Bj, we put 1. If this is 1, automatically this is also 1. So 1 into 1, the entry is 1. So here the entry 1 appears whenever the vertex Vi is adjacent to Vj. That means if there is a line between I and J, we are getting one entry, the entry as 1, otherwise the entry is 0. So we are getting, corresponding to each line, we are getting one entry 1. That means the sum must be equal to the cardinality, the number of lines, which is actually the cardinality of E of G. Here the E of G, if you are not using this representation E of G, it is very good. Actually, I must have written directly Q. Then it will be more clear. Since it is equal to 2 into modulus of E of G, here E of G represents the number of edges of G. So the number of edges is actually it is equal to Q. So Q into the term is 2 into Q. So we are getting sigma I is equal to 1 to P lambda I square is equal to 2Q. Again, the next result is let G is equal to B comma E be an undirected graph with maximum degree as D, and the eigenvalues we write as lambda 1 greater than or equal to lambda 2 etc. greater than or equal to lambda P, that is non-increasing order eigenvalues of its adjacency matrix. Then we want to prove lambda 1 is less than or equal to D, where D is the degree, the maximum degree actually. The maximum degree. G is an undirected graph with maximum degree D. We want to say lambda 1, that is the highest eigenvalue is less than or equal to D, that we want to say. So we take B as an eigenvector with eigenvalue lambda 1, and the maximum of the eigenvectors we represent as V of J. So let G be the vertex with V of J greater than or equal to V of I for all I belonging to V of G. Then already we have this result, is right? Ax is equal to lambda I. So you just multiply by V of J. So lambda 1 V of J is equal to A V J. So it is equal to sigma over I. Here ABJ, if you take ABJ, the entries are equal to 1 only if there is a line between I and J. So you can write this as sigma over I, where Ij belonging to E of G. The meaning is ith vertex is adjacent to the jth vertex. So if there is a line, we are taking the entry. So sigma over I, Ij belonging to E of G, V of I. So, and this is less than or equal to V of I less than or equal to V of J. So we can replace by V of J. And if Ij is an edge corresponding to the jth vertex, that means, so corresponding to J, if first vertex is adjacent to this one, we get 1. Second vertex is adjacent to this J, then again we get 1. So how many vertices are adjacent to the jth vertex? That much number of summation we get. So that is how many times J is adjacent to some other vertex. That is degree of J. So the summation runs over degree of J times, so degree of J into V of j, and degree of j into V of j is d V of j we are taking. That is maximum I am applying. Degree is maximum of degree is d. So it is less than or equal to d V of j. So d V of j. Now we started with lambda 1 V of j. It is less than or equal to d V of j. So lambda 1 is less than or equal to d. So if G is, suppose we take G as a connected undirected graph with maximum degree as D and the largest eigenvalue is lambda 1 is equal to D. If we take the largest eigenvalue is lambda 1 is equal to D, then G must be a D regular graph. That means all the entries in each row we have to get the entry as 1 exactly d times. That means exactly d times in each row we have to get 1 means that must be G is d regular. Otherwise we won't get this condition. Next we are finding some bounds for the energy of gas, that is 2q. This is Maclaurin's bounds which is published from a paper published in 1971. That is 2q root of 2q plus p into p minus 1 b square by d power 2 by p is less than or equal to E of g, which is less than or equal to root of tpq, 2pq, where d denotes the determinant of the matrix A. So here we apply the Cauchy-Schwarz inequality. This is the Cauchy-Schwarz inequality, that is sigma is equal to 20p A B A B whole square is less than or equal to sigma is equal to 1 to p A square into sigma is equal to 1 to p B A square. So here we substitute A as 1 and B A as lambda I. Then we are getting left hand side is sigma is equal to 1 to p lambda I mod lambda I, that is A is 1, B A is mod lambda I. So 1 into mod lambda I, so mod lambda I the whole square we are getting. It is less than or equal to, here A is 1 and again here we are putting B A is equal to lambda I. So here we are getting, this is left hand side, if you take sigma is equal to 1 to p lambda I the whole square is, as we proved already, it is E of G, energy. So it is E of G. E of G the whole square. By definition of energy of G, this one is the definition of energy of G. So E of G, this is E of G the whole square and it is less than or equal to this summation. This is summation of 1 p times, so p, and this is summation of I is equal to 1 to p lambda I square, and again this we proved in the previous one as modulus of E of G, that is q. So 2p into q. So here we are getting sigma is equal to this E of G square is less than or equal to 2pq. So E of G is less than or equal to root of 2pq. And next we consider E of G square at the other side of the inequality to prove. So we take E of G the whole square is equal to sigma I is equal to 1 to p modulus of lambda I the whole square. So again this can be written as split up into 2. That is lambda I the whole square. That is A plus B the whole square. Just imagine. Here we are having instead of 2 terms, p terms we are having. So 2 terms means we write first A square plus B square plus 2AB like that. Here instead of 2 here, so first A square plus B square. So here p terms, so lambda I the whole square. So sigma is equal to 1 to p modulus of lambda I the whole square. And here we write all the products since we are having p terms. So sigma I not equal to j. Here ij runs over 1 to p modulus of lambda I into lambda j. So again this is the first term is 2q, and just now we proved, so this is 2q plus the second term as it is. So now we use the fact the geometric mean cannot exceed the arithmetic mean. So this is the arithmetic mean. That means the arithmetic mean is greater than or equal to the geometric mean. So this is the arithmetic mean. Sigma I not equal to j, lambda I lambda j. How many number of terms we get? I varying from 1 to p. So j not equal to I கொடுக்கும்போது same value of I repeat ஆக முடியாது. J varies from 1 to p minus 1. So total number of terms வந்து p into p minus 1. So arithmetic means, so we are taking in the division. So 1 by p into p minus 1 sigma I not equal to j modulus of lambda I into modulus of lambda j, and it is greater than or equal to product I not equal to j. Here we are applying the geometric mean. Mod lambda into lambda power j we are writing the number 1 by n in the power. So now this is sigma I is equal to 1 to p, lambda is square power p, sorry, lambda is square p minus 1 times into the whole power, and the whole power is 1 by p into p minus 1. How we are getting this one? Again, this lambda I, lambda j, as I mentioned earlier, you have to take lambda 1, lambda 2, lambda 1, lambda 3, etc. If you are writing lambda 1 into lambda 1 மட்டும் இருக்காது. So lambda 1, lambda 2, lambda 1, lambda 3, lambda 1, lambda 4, etc. Similarly, second term, if you take lambda 2, lambda 3, lambda 2, lambda 1, there will be, lambda 2, lambda 2, there will not be, and lambda 2, lambda 4, 4, etc. So each lambda 1 if you take, then lambda 1 into lambda 1, there will not be other p minus 1 terms. Similarly, the next one, lambda 2, if you take lambda 2, there will not be, but we will have lambda 2, lambda 1, lambda 2, lambda 3, etc. Again, here p minus 1 times. So in every one, we are having p minus 1 terms. So if you take lambda 1 outside, lambda 1 into lambda 2 plus lambda 3 plus etc. lambda p will get. So if you take the summation, in the first summation, lambda 1 is not there. So it can be written as trace minus lambda 1. Trace is 0. So 0 minus lambda 1. So we have just lambda 1. This applying I is equal to 1, we take lambda 1 into trace minus lambda 1. Trace minus lambda 1 is, trace is 0, so minus lambda 1. So lambda 1, lambda 1, so we get lambda I 1 square. Similarly, the same procedure for lambda 2, lambda 3, etc. If you are applying, we will get lambda 2 square, etc. we get, and exactly totally p minus 1 terms. So we are having into p minus 1, lambda I square into p minus 1, whole power 1 by p into p minus 1. So this is product I is equal to 1 to n mod lambda I. Simplifying the powers, we are getting whole power 2 by p. So here this can be written as this product I is equal to 1 to p lambda I. We know it is actually the determinant of the matrix. So determinant of A of g power 2 by p, which is equal to d power 2 by p, where d denotes the determinant of A of g. So now we are having 1 by p into p minus 1, the left hand side. Sigma I not equal to j mod lambda I, lambda j is greater than or equal to d power 2 by p. So sigma I not equal to j, lambda I, lambda j is greater than or equal to, bring this p into p minus 1 to the next side, p into p minus 1 d power 2 by p. Now use this relation in equation 2. So take this as 3 and substituting in this 2. So substituting in this 2, we are having E of g is greater than or equal to 2 2q plus p, sorry, 1 plus is minus missing. So 2q plus p into p minus 1 d power 2 by p. So square, if you remove the square, E of g is greater than or equal to, here we have to take the square root. So we got both the relations. So root of 2q plus p into p minus 1 d square by power, this d power 2 by p is less than or equal to E of g less than or equal to 2. And this is another inequality which is proved by Caprosi, Fetscovi, and Goodman and Hansen. In the year 1999, E of g is greater than or equal to 2 root q. Again, we leave the remaining part, just it is greater than or equal to 2 root q. E of g the whole square is, just if you apply the formula, E of g the whole square is as in the previous one, it is equal to sigma is equal to 1 to p mod lambda I the whole square, which can be written as sigma is equal to 1 to p lambda I the whole square plus sigma I not equal to j mod lambda into lambda j. So this is equal to, this is 2q and this is 2 into sigma I less than j mod lambda I lambda j. So now E of g the whole square is greater than or equal to, that is here sum of modulus we are having. Now we are checking the modulus of the sum, so we can put the sign greater than or equal to. So E of g the whole square is greater than or equal to 2q plus 2 into modulus of sigma I less than j lambda I lambda j. It is equal to the first term is 2q. Again, just now we have seen this is also q, so it is equal to 2q, which is actually 4q. So E of g, if you take the square root, it is greater than or equal to 2q. And again, in 2001, Goodman proved this result. That is, if G has no isolated vertices, then E of G is greater than or equal to 2 into root P minus 1, and equality holds for stars. So if you take G is connected, then M is, that is, if it is a connected graph on P vertices, we need at least 2 edges. That is, in trees we must have studied, isn't it? So we have, without this minimum number of edges, the graph cannot be connected. So G is connected. So this is not M, actually Q. Sorry, Q is greater than or equal to P minus 1. And E of G is greater than or equal to 2Q, which is actually greater than, as from the previous result. This is from the previous result. So it is greater than or equal to 2 into root of p minus 1. And this result holds for q is equal to p minus 1. Then in that case, we get the equality sign. If it is greater than or equal to, we put greater than or equal to, and it is equal to means we use equality sign. And G is disconnected with n components. This is the connected case. If it is disconnected with n components, then for each component, suppose the components are having P1, P2, etc., Pn vertices, then it is greater than or equal to 2 into root of P1 minus 1 plus P2 minus 1, etc. we are having. So here the summation P1 plus P2, etc., that will be actually P. The remaining, so here root of P minus 1 and n minus 1 the whole square we are having. The remaining term, that is this 1, 1, 1, etc. also we are having. So it is greater than or equal to 2 into root of P minus 1 plus n minus 1 the whole square, which is greater than or equal to 2 into root of P minus 1. So now, if you take for a star graph, we are having equal to. So we are saying, so for the star graph, we have the minimum energy. And this G is a P comma Q graph with 2Q greater than or equal to P. Then E of G is less than or equal to 2Q by this one. So to prove this result, again we are taking Cauchy's first inequality, and we are taking I is equal to 2 to P. AI, BI, the whole square is less than or equal to sigma is equal to 2 to P ai square into sigma. Here we are taking the summation as 2 to P. That is the difference, main difference we have to notice. So it is less than or equal to 2 to P. Everything is 2 to P. Put I is equal to ai is equal to 1 and BA is equal to lambda I, and just on simplification we are getting the result, which is at the end. That is E of G is less than or equal to lambda 1 plus root of p minus 1 into 2q minus lambda 1 the whole square. At this stage, we take f of x as this function. Instead of lambda 1, we are taking x. So x plus root of p minus 1 into 2q minus x square. Take this as a function. Then this function, already in the from theorem, we are given one condition: 2p is greater than or equal to p, and this function attains maximum in a particular interval, and that interval is given like this. This function is decreasing, that is f double dash of x will be negative, so the function is decreasing in this interval. So if it is decreasing in that interval, then the values in the interval, actually lambda 1 lies between root of 2q by p and root of 2q, the function is decreasing function. So 2q by p less than or equal to lambda 1 implies f of lambda 1 is less than or equal to 2q by p, since it is a decreasing function. So we have f of lambda 1 less than or equal to f of 2q by p. So now substituting in the previous equation, we are having, that is here. If we are substituting lambda 1 badala, we can substitute the value. So here f of 2q minus p E of g is less than or equal to 2q by p plus p minus 1 into 2q minus 2q by p the whole square. So f of lambda 1 is less than or equal to f of 2q by p. So this holds for lambda 1 is equal to equality goes for lambda 1 is equal to 2q by p. Actually, just here we are applying the function is a decreasing function. Only using that fact we are able to prove the result. Next, Poolen and Moulton in 2001 proved this result. That is, if G has P vertices, then E of G is less than or equal to 1 by 2 into P into root of P plus 1. Now, suppose G is a graph with 3 vertices and 2 edges. If 2Q is greater than or equal to P, then this result we proved just now. E of G is less than or equal to 2Q by P plus root of P minus 1 into this one. Again, here we are going to see this function. If we consider this one, the right hand side as a function of Q, then it is maximized when Q is this value. So it is maximized. So E of G is less than or equal to, we can write. So when Q is this value, it is maximized. So substituting this value of Q, I didn't give the simplification here. If we substitute this value of Q in the right hand side, we are getting E of G is less than or equal to 1 by 2 P into root of P plus 1. Similar results actually following. So Poole and Moulton in 2003 again proved the result as E of G is less than or equal to 1 by 8 into this one. Here also he used this fact, that is Q is maximized. That is the function of Q is maximized when Q is equal to this one holds. So substitute Q is equal to this one in that equation. We are getting E of G is less than or equal to 1 by root 8 into P into root P plus root 2. Just substitution and simplification. I didn't give all this simplification here. Next, we are having another theorem that G is equal to P comma EB any simple P comma Q graph. If the E of G is a rational number, if E of G is a rational number, then E of G cannot be an odd number. If it is rational, it cannot be an odd number. So it cannot be an odd number, so it is enough to prove it is a even number. So to prove it is an even number, first we take the spectrum, that is lambda 1, lambda 2, etc. Lambda p be the spectrum of the matrix E of G, and we take these are positive and the rest are negative. Among the spectrum, we take the positive as first t values and the rest as the negative values. So now if we take sigma is equal to 1 to p mod lambda I, it is equal to lambda 1 plus etc. lambda t, and the remaining are negative, so we are taking minus of these values. So sigma this is equal to 2 actually here lambda 1 lambda 2 etc. lambda t. If we are adding here also, we have to subtract also, isn't it? So here adding here, that is within here we are adding means we are subtracting. So lambda 1, lambda 2, etc. lambda 2 t we are subtracting and taking here. So it becomes lambda 1, lambda 2, etc. lambda t. And here we are adding. So this is twice. So 2 into lambda 1 plus lambda 2, etc. lambda t minus this one. And this is sigma lambda I. And this is 2 times this one. So E of G is 2 into lambda 1, lambda 2, etc. lambda t minus this one. So that is E of G is 2 times something, and this is the trace. So it is equal to 0. So 2 times something. So it must be an even number. So E of G is congruent to 0 mod 2. That is, it cannot be an odd number. Similarly, we are having many results. Most of the results we are having, the bounds or results, they are related to the algebraic uh, formulas. So algebraic corresponding to various algebraic formulas, we are getting various bounds for this energy of graph. And okay, so I think I could skip these results. Yes, similar results only. So you can go through. Many papers are in energy of graphs. If you are going through all those papers, we are getting these results. All that is which are from algebraic formulas. All these are yes, similar ones. They will be boring if you are taking in online. So I am skipping. Okay. Now come to a new term, that is total energy. Actually, one of my scholar introduced this one. We are having corresponding to the adjacency matrix, we defined eigenvalues and correspondingly we are getting one energy. Similarly, corresponding to the given graph, if you are able to define any matrix, then corresponding to the matrix, we can define one energy. So here we are giving the total matrix. Total matrix is defined considering both vertices and edges together. So the matrix order will be P plus Q, P vertices and Q edges. So P plus Q vertices. Sorry. The rows, number of rows and columns will be P plus Q. So P plus Q rows and P plus Q columns, and they are representing. So in any row, first P values corresponding to, actually here we are not going to take first vertices and then edges. We are taking as vertex, edge, etc. So first vertex, then one edge, and next vertex, another edge. So like that we are giving, and the total matrix, the entries are defined like this. That is, we are considering the cases. These are the cases we consider. That is, two vertices are adjacent or two edges are adjacent. Then in that case, the corresponding term is 1. And also, vertex is instead with the particular edge. The corresponding entry is 1. And edge is instead with the particular vertex. The corresponding entry is 1. And 0 otherwise. So if no such instance, we are getting zeros. So corresponding to this one, we are getting one matrix, and that matrix we are calling as the total matrix, and corresponding to the total matrix, we are finding one energy. Here the number of eigenvalues, which is equal to the order of the matrix, that is the order of the matrix here is P plus Q. That is P plus Q rows and P plus Q columns. So we take it lambda 1, lambda 2, etc. Lambda P plus Q as the eigenvalues. Then corresponding total energy is sigma is equal to 1 to P plus Q mod lambda I. I have taken this one only because to say how to get the, how to use the MATLAB. That is, to use MATLAB, we have written a program. So before program, we used to write one algorithm. So what are all the steps we are going to follow? So we take a matrix, we take a graph first, and corresponding to the graph, we have to assign the total matrix. So these are the total matrix assignment. The entries of the matrix should be assigned, isn't it? So they are the these steps. Step 3 to this one. They define the entries and assume other entries are zero. So all the entries are given. Then we have to find the eigenvalues. Then the total energy. Now this is the MATLAB program. So percentage. Normally this is the comment line. So these lines tell us what T represents the total matrix, K represents the eigenvalues, and T represents the total energy, and the order is P plus Q. And PQ represents the number of vertices and edges of CP. And these are the assignment statements. So these are written using MATLAB format. So the syntax which is to be used in MATLAB, that is followed here. So now we assigned all those values. Then just give this one, which is enough. K is equal to IT. That is, eigenvalues of T will be stored in the name K. So if you want to print K, just if you give K, then eigenvalues will be printed. Very simple thing. You have to give the entries only. If you are giving the entries carefully, we give the corresponding eigenvalues, and next we could find the corresponding energy value. So here we call the name as total energy. So this, using this method, we can find it for any graph and also with any number of vertices. So in the program, we are writing P plus Q. If we are varying the values of P and Q, then if it is P plus Q, if P is 5 and Q is some 3 or 4, give the corresponding matrix entry, we give the corresponding total value. So for giving finite values, we can generalize that one. So generalizing the characteristic polynomial, we can solve that one, and then we can find the eigen values. So that is written for two more graphs. That is dumbbell graph also. We have written the algorithm and then the MATLAB program. So using the MATLAB, we are able to find the total energy, and then Okay. Now the next, the next one is, it is two graphs. Some more facts related to energy. Two graphs are said to be, two graphs are said to be co-spectral if they have the same spectrum. That is, spectrum is the set of eigenvalues. So if they have the same set of eigenvalues, we call them as co-spectral. And also, two graphs are said to be equi-energetic if they attain the same energy. So if we have co-spectral graphs, obviously they will be equi-energetic. So co-spectral, the next one is actually wrong. Co-spectral implies equi-energetic, but the other one is not necessarily true. Next, if two graphs are isomorphic, then they are co-spectral and equi-energetic. பேசுறது clear கேக்குதுல்ல? Am I audible?
Yes, ma'am. There was just 1 second pause. You're audible now, ma'am.
Okay.
Ma'am, we can't hear you now. Ma'am,
Yes. Is it okay now? Is
yes,
it okay
ma'am.
now? Yes. So from complete
Yes, ma'am.
graph, we are going.
Yes, ma'am.
Yes, sorry. From complete graphs, we are going to obtain equi-energetic regular graphs. So now, by deleting some edges from the graph, we are getting one d1 of k2p. That is, consider the graph obtained by deleting the edge joining the vertices I and p plus I from k to p. So we are taking complete graphs with 2p vertices, even number of vertices, and we are deleting these edges I and p plus I. So if we are deleting these edges, then we are getting a resulting graph, and that resulting graph is found to have 2p into 2p vertices and 2p into p minus 1 edges. One example is given here. When p is equal to 3, this is k to p, that is on 6 vertices, complete graph, and d1 of k6 is this graph. Now k to p and d1 of k6, if you consider d1 of k to p, the energy is actually equal to 4 into t minus 1. So it is found in the usual method as I mentioned earlier. So it is found to be 4 into t minus 1. And then from d1, we are getting another graph d2. Let us split the vertex set into two equal parts. Consider k to p, split the vertex set into two equal parts, delete the edges between those splitted parts. The resultant graph is disconnected graph with two components and is denoted as d2 of kp, k to p. The graph looks like this for p is equal to 3. So for this graph, once again we are finding the energy, and the energy is once again equal to 4 into t minus 1. Obviously, this graph is not isomorphic to the previous one. The eigenvalues may or may not be the same, but they are having the same energy. That is important here. So these two are equi-energetic graphs. Similarly, we are removing some more edges also, and we are proceeding to get d3 of k6. There also we are finding 4 into p minus 1 as the energy level. And join of some complete graphs. Here also we are finding the energy. Once again we are getting the same one. Now just we are having a conjecture, that is among graphs with p vertices, The complete graph Kp has the maximum energy equal to 2 into P minus 1. It is conjectured, but it is disproved by this Watson. That is, Kp is not the graph with P vertices having maximum energy. There are some other graphs on P vertices which is having energy greater than Kp. So it is disproved by Chris Watson. And such graphs we are calling as hyper-energetic graphs. That is, a graph G having energy greater than the complete graph on the same number of vertices is called hyper-energetic graph. So a graph G, that is once again it is very defined. That is, for complete graph the value is 2p minus 2. So energy is greater than, the energy is 2p minus 2. So if G is a graph whose energy is greater than 2p minus 2, then, but they are having the same number of vertices, then it is said to be hyper energetic. And G has more than 2p minus 1 edges, then line graph, if you take the line graph of G need not be hyper energetic. That is, this is another result. That is, the line graph, if you take the line graph need not be hyper energetic. Line graph would have energy may be less than the energy of K to P minus 1. If G is a complement of a regular graph G, then G is non-hyperenergetic. Similarly, if G is a complete bipartite graph, all these results are proved in different papers. If G is a complete bipartite graph, then G is non-hyperenergetic. Similarly, all cubic graphs are non-hyperenergetic. And Goodman et al. Performed a useful experiment. The experiment is they started with Kp and added edges one by one uniformly until end up with Kp. Kp complementல start பண்ணி edges add பண்ணிட்டே வராங்க. Adding the edges, they proceed till they end with Kp. And at each stage, they are finding the energy. But they are able to get this result. That is, the expected energy of a random PQ graph first increases. That is, we are adding the edges. By adding the edges, the energy is getting increased in the beginning and attains a maximum value at, after some edges. And that number of edges we take as Qmax. And after attaining that stage, it is going on decreasing. So always addition of an edge need not increase the energy. That is the observation here. Goodman et al. Performed this experiment. So the energy need not increase always by addition of a edge. Again, this is a line graph result. And next one is hypoenergetic. A graph G on P vertices is said to be hypoenergetic. If energy of G is less than, then it is said to be hypoenergetic. There are some graphs given as energetic, hypoenergetic and non-hypoenergetic. Some theorems are also proved. Now, so we started with the adjacency matrix, and from the adjacency matrix, we got the energy of a graph. Then many people started giving different graph matrices, and corresponding to each of those graph matrices, they found an energy, and correspondingly they named them also. These are several energy concepts which are already in different papers. That is ABG energy, ABC energy, accurate independent dominating energy, additive color Laplacian energy, Albertson energy, arithmetic geometric energy, average degree energy, color energy, etc. etc. We are having a lot number of papers on energy. Some of the definitions I have given here, the Laplacian energy. Here, so energy we are giving means we have to give one matrix. So the Laplacian matrix is defined first. It is defined as L of G is equal to D of G minus A of G, where D of G and A of G denote the degree matrix and adjacency matrix. Degree matrix corresponding to each vertex, we have to give the degree. So degree matrix and this one respectively. So corresponding to this, we are getting the Laplacian energy, and that is proved like this. It is equal to sigma is equal to 1 to p modulus of lambda is equal to lambda I minus 2q by p, where lambda I is the Laplacian eigenvalues of G. Similarly, extended adjacency energy, that is defined like this. So that the extended adjacency matrix is defined like this. Corresponding energy is named as extended adjacency energy. Randic matrix is defined as 1 by root of degree of Vi into degree of Vj, Va, Vj are adjacent and 0 otherwise. And the corresponding energy is defined as Randic energy. Similarly, distance. If Vi, Vj are adjacent, then corresponding distance value is taken. And the matrix is named as distance matrix. And the energy is called distance energy. Okay. We are having many more. Those who are interested may go through all those energies. So, degree sum, product, Netor, etc. etc. So, with this, just I have given some introduction to the energy. Those who are interested may go through. We are having more than 100 papers. Only 100, you can say 200 I think. So more than 200 papers in this area. So any people interested may go through those papers and may work on these results. Thank you. Thank you for giving me the opportunity.
Thank you, ma'am. Participants, if you have any questions, please do post them in the chat box, YouTube chat box. Ma'am, I have a question. May I ask?
Yes, 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 yes.
Why is the name energy given to this definition? Is there a physical interpretation?
Yes, yes, yes. Actually, it is connected to the energy in chemistry. The derivation is only from that one.
Oh, okay.
Already I informed in the beginning. So the energy level
Yes.
of electron, it is used to calculate the energy level of electrons. Only from that concept it is derived. So it is named as energy.
Okay, so it can be translated to matrices and then calculated.
Yes,
Okay.
only with the matrix it could be found out.
All right, ma'am. Thank you.
Yes,
Ma'am,
yes,
this is Professor Jackson. I have a question, ma'am.
yes,
Uh,
yes, yes.
Ma'am, is there any program, computer program can be used to find this energy of graphs?
Actually, MATLAB is that no computer program, and also there are some free websites. That is, they are giving for 35 days free version like that. There also you can find directly the polynomial and also this one.
Oh, thank you, ma'am. Thank you. So there is a question from YouTube chat box. Ma'am, what are the real world application for this energy of graphs?
Yes, in
Chemical graph
chemical
theory. Yes.
theory actually. Yes,
Yes. Yes.
only derived from that
Chemi-
chemical results.
oh, okay, ma'am. Okay, ma'am. Okay, ma'am. Thank you, ma'am. Thank you.
Stop screen sharing.
Ah, yes, ma'am. Yes, ma'am. Thank you. So now, if there is any other question, you can ask now in your YouTube chat box, and also the Google Meet people. If you have any question, you can ask now. Okay.
குயிக்கா முடிச்சிட்டேனா
இல்ல மேம் ப்ராப்பர் கரெக்ட் டைமிங்.
இல்ல இல்ல கரெக்ட் டைம் தானே எஸ் எஸ் அதுக்காக தான்
ஒன்
கொஞ்சம்
ஹவர்.
ஃபாஸ்ட்டாக ஓட விட்டேன்
ஓ அப்படியா? பட் ஸ்டில் யூ
இல்ல
ஹாவ்.
இல்ல அது அவ்வளவுமே மோரோவர் இட் வில் பி போரிங் ஆல் தோஸ் ரிசல்ட்ஸ்
No, ma'am,
ஆன்லைன்
no, ma'am.
மீன்ஸ்
It's somewhat interesting because in your talk you have told that some conjectures which you have disproved. So it is the real essence of research, and also it will pave a pathway for them, the budding researchers, how to
எஸ்
they lead
ஷார்
their
ஷார்
research. Thank you, ma'am. Now I request our assistant professor, Dr. Safina Devi, to give the vote of thanks, please.
Yes. Good evening, everyone. It is my privilege to propose the vote of thanks today. On behalf of everyone, I would like to express our sincere thanks to our speaker, Professor Dr. K. Parani, for introducing to us the concept of energy of graphs and giving us excellent coverage over the topic. You also taught us how to calculate the energy and give bounds for different graphs, and showed us a MATLAB program to demonstrate the working process of these calculations. I hope this would have provided sound motivation for researchers who are working on or are planning to work on algebraic graph theory. Thank you, ma'am, for enlightening us with your explanations. I extend my hearty thanks to all the participants and everyone else responsible for the successful conduct of this program. Thank you, one and all.
Correct.
Thank you, ma'am, once again.
Screenshot.